Periodic trains are patterns in elements on the periodic table that shows different aspects of elements like their size and its electronic properties. They are necessary because they show their similarity atomic structures of the element with their families or periods. They have 7 trends that are the following: electronegativity measures an atom tendency to attract and form bonds with electrons from the left to right. Across a period of elements it increases from top to bottom, down a group decreases. Noble gases have an exception to this rule. And transition metals, although they have electronegativity values, there is a little variance among them across the period and up and down of the group. The element with more electronegativity is fluorine.
First, we have the ionization energy, which is across a period, and the ionization energy generally increases from left to right across a period. The trend is attributed to increasing effective nuclear charges as the number of protons in the nucleus. Electrons are also added to the same principal energy level and increases to pull them closer and make it difficult to remove each other. And then we have the down a group, which is decreases from down a group is caused because as you move a group down and the additionally energy levels are added, and it increases the distance between the outermost electrons and the nucleus. The outer electrons are a shield of inner electron shells, reducing effective nuclear charges, and that means that they are less tightly held and they are easily removed and acquire less energy from ionization. Next, we have the electron affinity. We have also two across the period, which is becomes more from negative, also named exothermic. And as you move left to right, the atoms on the right side of the periodic table have almost completed the valence electron shells and are more like to find the electrons to achieve a stable electronic configuration. Then we have the down group, which is generally from a less negative or a positive down group. And as you move down a group, the atomic size increases and the outer electrons are more further for the nucleus, and it becomes hard to add an electron because of the increase of attraction. And we have the atomic radius, which is across the period it decreases from left to right, is because it increases the effective nuclear charge as the number of protons in the nucleus increase. The increased nuclear charge pulls the electron closer to the nucleus, reducing the atomic size. Then down a group, it increases down a group. Is additionally additional energy levels are added, increasing the distance between the nucleus and the outermost electrons. Is the result of a larger atomic radius. For the melting point across the period, we can have a very cross. It can vary across a period, but it generally increases from a maximum to a minimum. The metallic elements, for example, are typically a high melting point, and they tend to peak around the center of the periodic table. And then down a group, the metals have a high melting point, which it decreases if you move down the group. And mostly because the metallic bonds are weakened, and they increase the atomic size, resulting in lower melting points. Finally, the metallic character is across the period it decreases from left to right, and the metallic character is also associated with elements' ability to lose electrons and to form positive ions. As you move across the left to the right tendency, the tendency to lose those electrons decreases because the electronegativity decreases in the atomic size. From downward group, the metallic character decreases from downward group because as you move down the group, the atomic size increases and the outer shell electrons are further from the nucleus, and the result of it is that they are less tightly held and they are easily lost positive ions.
Hello, my name is Carlos Santiago Garza, and I'm gonna talk about chemical bonds. So, chemical bonds is a chemical process generated by attractive interaction between atoms and molecules. So, to stabilize compounds. In that process, it consists of exchange of atoms, like giving or losing atoms, or just like staying the same for the purpose of stabilizing the chemical compounds. There are various chemical bonds like ionic bonds, covalent bonds, and metallic bonds. So the ionic bonds are mechanisms that is based on the transfer of electrons. So in the ionic bond is to transfer an electron to another. It's to transfer electrons from a atom or a molecule to another. When the elements have different electronegativities, they do not bond. By sharing electrons, but by giving up electrons from the less electronegative element, which will form a cation, to the more electronegative, which will form an anion. This bound characteristic between metal and non-metal atoms. Okay, so that was ionic bonds. Now going with covalent bond, this bonding mechanism is based on sharing electrons. Okay, so as I said, it's by passing electrons from a molecule to another. They share electrons since the atoms that are bonded have a similar electronegativity. The bond is characteristic of the bond between nonmetallic elements. Okay, so that was covalent bond, and then I'm gonna go with metallic bond. The bonding mechanism is based on collectively sharing electrons between the atoms that make up the metal electron gas model. So yeah, that's the metallic bond. It's just by sharing electrons between the atoms that will make up metal and do have the properties of metal, and that's it.
Good morning or afternoon. We, Andrea Trejo and Maria Luisa Soto, are going to explain the intermolecular forces. Well, these are the forces that exist between molecules influencing the physical properties of substances. Firstly, it's important to distinguish intermolecular forces from intramolecular forces. Intramolecular forces are the forces within a molecule that holds the atoms together. such as covalent bonds. In contrast, intermolecular forces are the forces of attraction or repulsion between neighboring molecules. These are three types of intermolecular forces: London dispersion forces, dipole-dipole interactions, and hydrogen bonds.
Now I'm going to talk about the three types of intermolecular forces. We have first London dispersion force, that are the weakest intermolecular forces and are present in all molecules, whether they are polar or non-polar. They result from the temporary fluctuations in electron density within molecules, which create momentary dipoles. Even noble gases like argon exhibit these forces. The strength of London dispersion force increases with the size of the molecules. Larger molecules have more electrons, which can create stronger temporary dipoles. Then we have dipole-dipole interaction. These occur in polar molecules where there is a permanent dipole moment due to difference in electronegativity between atoms in a molecule. And then, for instance, in hydrogen chloride, the chlorine atom is more electronegative than the hydrogen atom, creating a dipole with a positive end at hydrogen and negative end at chlorine. Dipole-dipole interactions are stronger than London dispersion forces, but weaker than hydrogen bonds. Then we have hydrogen bonds. These are a special type of dipole-dipole interactions and are the strongest among the three types of intermolecular force. They occur when a hydrogen atom is bound to a high electronegativity atom, such as nitrogen, oxygen, or fluorine. The hydrogen atom becomes positively charged and can strongly attract the lone pairs of electrons on a nearby electronegativity atom. Water is a classic example where hydrogen bonds play a crucial role, giving water its unique properties, like high boiling point and surface tension.
Intermolecular forces are critical in determining the state of matter, solid, liquid, or gas, at a given temperature and pressure. For example, water H2O is a liquid at room temperature due to its strong hydrogen bonding, while methane CH4, which has London dispersion forces, is a gas. In summary, intermolecular forces, although weaker than intramolecular bonds, are essential in dictating the physical properties and behaviors of substances. Understanding these forces helps explain why different materials have varying boiling and melting points, solubilities, and other physical characteristics. Thank you for listening, and I hope you now have a clearer understanding of intermolecular forces and their significance.